Okay, sure.
Hello.
Okay,
Okay,
good.
so I started recording.
Sure. For the cloud one, the previous one you sent, there's an issue where they say I do not have permissions. So yeah, we might want to look into that later.
Oh, you don't have permission? Oh, wait. Okay, so I started recording.
Okay, awesome. Do you mind if I ask you a question about complex derivatives?
Yeah.
So I've seen this expression and I want to show that it's equals to this, but then I have difficulty showing the logarithm because I'm not sure what to make of this. As in, this term is kind of like z minus w z bar minus w bar.
Right.
I'm a bit confused why the derivative of ln of this thing is um oh well that uh okay, I guess it splits up into you can take the sum. Okay, I guess it kind of makes sense now. Yeah. Okay, never mind. That's a dumb question.
Yeah, because like you're treating z and z bar as independent variables.
Right. But I'm a bit confused also. So I have this, and then now I can see that it
Yeah.
equals to this term over here. But I'm a bit confused about things in general where um when they say so from what I understand, if f of z is if f of z is holomorphic, right, then if f of z is holomorphic, then the basically the so-called usual rules apply
Yeah.
of complex differentiation. But if f of z could be meromorphic, so I'm talking about so f of z being holomorphic would mean that the the anti-holomorphic derivative of f is zero, but
Yeah.
that isn't the case where if f of z is not holomorphic, so something like that. And I heard that is equals to z minus z bar. I'm not sure if there's a factor of 2 pi. I'm not sure what to make of this exactly. Um,
The
yeah, do
delta
you know?
function?
Uh, more of the left hand side. How does one I know people use the Stokes theorem and things, but um
Ah,
I, it's not
yeah.
enough for me.
Wait, where are you writing this? Let me just find
Okay,
it.
let me pull up the link. Um,
No, like where on the
the
whiteboard? I'm confused.
okay. Let me
This whiteboard can really go some places.
yeah. Um,
Oh
it
yeah, I
is
found it. I found it.
okay. Great. Yeah, I came across this post, and then they mentioned about something about Stokes theorem, but I barely know how to treat the left hand side of this because I don't really know that much differential forms.
Huh. Wait, let me uh okay. Wait, let me just check. Uh uh right. Okay. Yeah. Wait. Looking at wait, it's not wait, could you like go back?
Sure, to this.
Yeah. Delta, no, it's not minus, it's delta comma.
Oh, I
Well,
see.
it's
Oh,
not
that's a
minus.
I see. Okay,
That's a
sure,
very
sure.
big difference.
Oh, okay. What difference does it make? Usually, this means if Z is directly wait if
No, this
yeah
is
that
this is z equals z bar equals 0.
ah I see. So Z minus Z bar. I see it now. So Z minus delta of Z minus Z bar is essentially saying uh this thing must be equal to zero inside, and that will
Yeah,
imply that Z equals to Z bar, which means that
yeah,
is Z this equivalent to saying real of Z delta of real of Z.
yeah.
Wait, sorry, delta of imaginary of Z. Uh, yeah, right. Okay, that makes a lot of sense.
Yeah,
Um,
okay. And I guess like when you have like delta functions like these, um, like technically speaking, like this side. Now, obviously, the real answer is that partial z of z bar is what 0, at z bar equals 0, or okay. And let me just at set nec 0 and partial z bar 1 over z is obviously undefined at z equals 0, obviously. I mean, but like it ain't. So
Actually, in general, when I talk about z and z bar, things like this somewhat confuse me whenever I see a differential like this,
yeah.
because whenever I'm in doubt, I always go back to the real coordinates. So yeah, but yeah, I'm basically not sure about Stokes' theorem on complex manifolds. Do you happen to have any good resources for that?
Wait, let me just. I mean, a complex manifold is just a manifold.
Right, with some additional structure.
Yeah. So like, okay. So the key to understanding this is that if you were like write z equals x plus y, on the manifold. So if you have a point on the manifold, and if you were to like map the point to x comma y by, God, I mean, my pen is a bit broken. My x comma y by a chart. The next x and y are real. There's no denying this. So just keep that in mind. But what the people are doing is just for the sake of handiness, like just for usefulness, they complexify the tangent spaces. That's what they're doing. So we can consider partial x plus I partial, god damn it, partial y, for instance, like yeah, my pen is a bit weird, but like you can consider these types of things with the I in there because we complexified the vector space. This is just
yeah, that makes sense.
So if you're yeah, that's just how it is. So Stokes' theorem is just Stokes' theorem.
I see. So perhaps if I expand the following on the in the original x and y bases.
Yeah, you might. Okay, let's actually see what it becomes. I'm curious.
Sure.
Yeah, yeah, that's good. Yeah. Then it will become much more tractable for you.
Right.
But the key to understanding whatever's going on here is that, like, if you complexify the tangent spaces, like literally all the theorems that you know, like all the theorems about what calculus on manifolds, you know, about calculus of tensors. So like tensor calculus, they'll still be the same. The reason why they will still be the same, is because when you derive identities about tensor calculus, if I recall correctly, I doubt that like I think deriving the identities of tensor calculus never really relies on the fact that the vector space is a vector space over the real numbers. Yeah, I think you can think that they are over the complex numbers. So you could like extend to that.
I see.
Yeah. For example, what would be a good example? Like if you were to like take a look at like Stokes' theorem, for example, then you can like go through the entire derivation just assuming that the vectors were complexified, and there would be
See,
like no problem at all.
I see.
So yeah.
Are there some fast rules that we can, when in doubt, we can always go back to the fundamental definitions, but is there some fast rules like saying, perhaps like saying, yeah, are there some fast rules that can follow? Like, you can say that we can get rid of this and this, they kind of,
Oh yeah, you
because
could.
from what I understand
Right.
now,
So you need to what you need to know is that if we were to complexify the tangent spaces, then partials then like z bar and z are totally cool like reperm like and like partial z bar and partial z are totally cool basis vectors. So like imagine that you have like x plus ay. I really should change my pen. This is insane.
sure.
Ay
Is it the
and
same
x.
tablet?
Yeah,
Are you
but the
still using
pen
the
is
same tablet?
acting weird. So if you have
I
x plus
see.
ay and x minus ay for a real,
Right. Then it just be another
then
coordinate.
yeah, this is just totally okay, right? These are two okay
Yeah.
coordinates. But like if you were, so we could define if we were to call this c. Oh no, this is terrible. C, if we were to call this d, then obviously we could consider partial c and partial d. That's totally fine.
Yeah.
But if we were to like
I run
complexify the tangent spaces, then A could obviously be complex, and you could still define the vectors partials C and partial D.
right. I think I might so in my equation, I kind of arrived at the fact that this derivative is zero. I'm not sure what went wrong.
Um,
I'm just blindly applying the normal
no,
calculus rules
it's
to it.
not zero
Yeah.
because it's not zero at the origin. This is the same. You're making the same mistake as assuming
Oh,
that
right.
the divergence of the electric field of a point charge is zero everywhere. It's not zero at the origin.
Right.
So you can't really
Hmm.
calculate this unless you actually use Stokes' theorem.
I see. Oh, okay. In that case, I think I know what to do. So instead of having this line, right? So this line is bogus, right? Right. Because we have a divergent term in the center. So
Yeah.
that's where we now we can apply Stokes' theorem to it. So we split up individually, and so I suppose this could be minus I, and then now we can take over the boundary. Partial of x dx would would um would would be the kind of I don't know, maybe this is right, dy, and partial of plus I partial of y dy can kind of eliminate each other. Wait, does this make sense?
I think
Do you
so.
think
Up to
so?
a sign is that's probably
What I'm
correct.
saying is that I'm basically saying uh this. Yeah, I'm basically saying this.
Yeah.
But I'm not sure if I take away the f for the dy, whether I pick up minus sign because okay, yeah, perhaps we can take. I guess we can give this a try, and um this would be I. If I bring in the minus I, then that will be. If I bring in the minus I, then that will
Just
be.
becomes integral 1 over z dz. Wait, did you make the sign error? I think you made a sign
Yeah,
error.
I think I made a sign error. So I think what's wrong over here is that when for the second case, right, it should be the boundary minus partial y because I need to flip this over. Yeah, that makes sense. So I flip this over, it picks up a minus sign.
Yeah,
So this would be a negative, and then this would be a plus, and now it makes sense. So
right.
yeah, I guess I've somewhat derived it. Even I find that when I do things like this, I'm
Yeah,
more or less just applying whatever rules I know and trying to
yeah.
hope that it works. And
Yeah, but the
eventually
key
kind
is
of
like you don't even need to do that because like all the theorems will still work even if you like complexify the tangent vectors and tangent covectors is all going to work anyway.
mm,
Um,
sure.
yeah.
Okay, great. I guess that's that's fine then. So yeah, sure. Okay, I guess we can talk about yeah, last week we left off talking about I remember you left off talking about I'm going to whiteboard 3.
Yeah. Okay.
Complex analysis is really rich subject,
I
but
mean
there's
it's
so
not
many
that
more
rich. It's not that or like
oh
I know like uh I mean it's very useful, but at the same time it's just Stokes theorem.
right.
Like even like the central theorem of complex analysis is just Green's theorem, which is just Stokes theorem.
Hmm, I see. Okay,
Like
so last time
yeah.
we left off
Um
talking about the UV and IR divergences.
right.
And
So we're here. And I guess I have to talk about the whole thing of like calculating this. I yeah. I'm just going to like here's what I'm just going to like throw a theorem at you, which I am not going to prove, but it's just
sure.
like Calc 1, so I don't really care about proving this. Um, let's
Yeah,
see here.
okay,
Oh,
sure.
where is my okay integral dnk 2 pi n k squared. Here I guess k squared would mean what? Like ki plus f minus I epsilon alpha, where I'm sure that yeah, so like sum over ki plus alpha minus I epsilon to the alpha is equal to I over 2 to the n pi to the n over 2 gamma alpha minus n over 2 gamma alpha f n to alpha, and the residue of gamma of minus n is equal to minus 1 to the n of m. And this residue basically means that if you have a pole, then residue c over z is c.
Hmm, sure.
Yeah, so this is nice. This is useful. So let's calculate whatever we were working with. So what were we doing? We were doing something. I guess we were doing
You're
yeah,
calculating
we were trying to calculate this dude. I think this was what we were trying to get at. Um,
delta square of 0, right?
yeah.
Yeah,
And
right.
this was just like this thing. But you were gonna cheat and we're gonna calculate, we're gonna call this F. F2 and do 2 comma 0. And what we're actually going to calculate is FD comma let's call it elf n comma m squared. Uh and this is wait, let's just control notation. We're gonna calculate fn comma f. And this is just going to be uh well does this thing have oh It does have copy paste. Copy. Paste. Oh god. Paste. Why doesn't it paste where I want it to? Okay, here we go. Okay, so this is just
That's
this.
cool. Sure.
But like alpha is now 0. Yeah.
Mhm.
Okay, so and we're gonna write. This is going to be very underwhelming, so you have to be prepared. Whoops, I left loci. Just a second. This is going to be extremely underwhelming. We'll see here. I'm logging in again. This might take some time, but okay.
Okay.
Everyone watching this video can try to guess what the answer is. The answer is unbelievably stupid, but that's just how things are in life. Still loading. Did you know that MIT internet is not really good these days? It's just
Oh,
how life
I see.
goes, I guess.
Oh, you're back there?
Hmm?
You're back in MIT?
Yeah.
Not in Korean, no? I see. When does your like lesson start?
It started a long time ago. Well, not long. About a month ago, I guess.
Hmm.
Whoops.
Oh,
All right. I'm
are
back.
the okay, sure. Are the modules you're taking fun?
What?
Are the modules you're taking fun?
I can't really hear what you're saying. I'm sorry.
Oh, I think the internet is probably slow.
Okay.
I
Yeah.
oh, I think
Uh.
my
Wait.
yeah. Okay, I'm back. Yeah.
Okay. Yeah. Cool. Wait. Let me just check one thing. Let me just pause the recording and check something. Okay, let me continue because there's something that I would like to point out. This equation that I wrote here, it's not really optimal, and let me explain why. Like, let me just try to fit. So, okay, so let me pause again and just. Okay, so I should really like change my notation because this is kind of stupid. Let me rewrite this because this is kind of dumb. We're gonna do everything in Lorentzian. No, we're going to do everything in Euclidean, in like Euclidean
Sure.
convention.
Euclidean metric. Okay.
So it's really important that I write everything in a Euclidean way. Okay, so this is the correct answer.
Mhm.
You can check that this is the answer. Yeah, but anyway, when the thing with the I epsilon and all that, that was just like Lorentzian stuff with regurgitation, but like these
I
days,
see.
obviously, I'm a math dude, so I like to do everything in the Euclidean case, which is
Mhm.
nice because though you don't have some
Oh, yeah.
weird dimension that has a weird minus sign in the metric. So yeah, if we were to do this calculation, we just need to plug in a few things. Well, alpha is 0, so what we get is incredibly dumb, but like it's cool. We get 1 over 2 to the n pi to the n over 2 gamma 0 gamma minus n over 2 then you get f n over 2. But the thing is, we're going to analytically continue this. But the weird thing is, so basically, no matter what n is, this is gamma 0. Because gamma 0, wait, is always. Wait, did I get this right? Yeah. Okay. So what? Wait, let me check what. So according to the gamma function, gamma 0 is always infinity.
It's 1 plus 1 plus 1 plus 1, right?
Yeah, so this is just always 0.
Sure. But what if
Your
the
internet is kind of slow. Okay, yeah, now it's appearing. So
what if
if we analytically continue this is very dumb, but the
then
value
what
of
if the
delta square
numerator
0 is 0.
what if the numerator is 0? Sorry, what if the numerator is infinity? Then
Well, the thing is, whenever the numerator is not infinity, which is like in almost everywhere except some integer points, right? So like the key idea here is that what we did is that we had the UV and the IR divergences. We cured the IR divergences using F, and we cured the UV divergences by actually assuming that n was 2 minus epsilon. At least that's what I think is the usual way to do things. Let me just check. Okay, yeah. So if n is 2 minus epsilon, where epsilon is small, gamma minus n over 2 is something along the lines of 1 over epsilon, but it's not 0. But it's not infinity. Meanwhile, gamma 0 is like obviously infinity. So this has to be 0.
Sure. All right.
So we've learned an important lesson. This is stupid, but the delta function is 0 whenever x isn't 0. But even when x is 0, the value of the delta function at 0 is 0. So the delta function is the constant function which has value of 0. But if you integrate over it over some region that contains the origin, you get 1. Now I'm just joking. Obviously, I'm joking. Obviously, the delta function is not constantly 0. But I'm just saying that if you regularize things, which is how things are defined in QFT, the delta function has value 0 at 0. But some things may not have value 0. Let me give an example, I guess, of something that might not actually be 0. This is like one of the central identities of the one of the central identities, I guess you could say, of delta, like of QFT and like beta renormalization calculations and all that. Yeah, so let's see here. Let's try to calculate. Let's see. So, okay, so we define the inverse of the Laplacian as using this identity. Let me actually try calculate delta, the inverse Laplacian of delta squared at 0. Was what? Okay. This is a fun question. This is actually non-trivial. To solve this, we just write this in like what, the Fourier picture, which is just equal to, as we shall soon see, is equal to this.
Okay.
But this is basically just the case. Now we're going to like apply our trick. Okay, so wait, let me just make it clear what we're doing here. So it's this. Now we're gonna put a red equal sign, which implies that we're going to put our tricks into play.
The denominator also n is 2.
Yes. Oops, sorry. Okay, now we're going to do a trick and we're going to like do the usual weird things. So we're going to replace 2 with 2 minus epsilon. And we're going to put in an f here.
All right.
Now, obviously, we're going to put f equals 0 later on. Now, if you can see this, This is equal to 2 to the 2 minus epsilon. You have to keep the factors of epsilon. We might have to, just in case something happens later on. We get this. And now, gamma 1 minus 1 plus epsilon over 2, and we get gamma 1. Yeah, that's what we get. And no, wait, with one last thing. F to the and 1 over epsilon divided by 2. And okay, we need to actually take a step back and do some more stuff. So this is really physics math, but over here, if you take a look here, you see that the dimensions don't match. So like assume that we're going to give k dimensions of length inverse.
Mhm.
This whole thing is basically length 0 dimensions.
All right.
But if you look at this whole thing over here, you can see that this has dimensions of length minus epsilon, or length plus epsilon, actually.
Mm.
So this is bad, because in physics, you can never say that two quantities that are equal have different like dimensionalities in terms of like units and stuff. So we're going to actually have to insert a tricky parameter called mu here, where mu has dimensions of length inverse.
All
And
right.
so we see that over here, we will get mu to the epsilon over here.
Okay, sure. This
Um,
is before taking epsilon to 0. Yeah.
yeah. And wait, let me. Oh, wait. Oh yeah. This is actually just f minus epsilon over 2. Okay. And then we see what we see here is that this is just equal to 2 minus epsilon pi 1 minus epsilon over 2 1, and then this becomes 2 over epsilon actually, and this becomes mu over square root of f epsilon. So like if we were to like do the full thing, you get 4 pi over 1, then you get 2 square root pi mu over square root f. So epsilon 2 over epsilon. So that is what we get here. And you can write this out further, I guess. And then you get 4 pi over 1, 2 pi, 1 over epsilon, plus 1 over 2 pi log 2 square root pi mu over square root f plus dot dot dot.
Oh, hold on. The logarithm appears because
Epsilon is small here.
sure. So you're
we're
taking the limit, and that's kind of the definition of
yeah. I Taylor expanded this part.
Oh, about um Wait, the Taylor expansion of 1 of x to the epsilon is, I'm a bit confused about this step. Taylor expand x to the epsilon.
Yeah.
Yeah, I'm a bit confused about this.
Why?
Are you Taylor expanding about x equals to
No, I'm
0
Taylor expanding around epsilon equals 0.
around epsilon equals to 0? Oh, okay. So this can be written as uh uh exponential of right. So epsilon ln x. Okay, that makes a lot of sense. Yeah. Okay.
And I
Sorry for that.
think,
Yeah.
okay, so like, so let's see, we have to send square root of f to 0 here, but as it turns out, if we do calculations, if we do like real physical calculations, this square root of f will cancel with some other square root of f somewhere else. So we're gonna
Mhm.
leave it here for now.
Mm.
And as we can see, there is an epsilon here. So that's pretty
Mm.
non-trivial, if you ask me. And then you have mu here, which is a bit weird. We don't really know the meaning of the parameter mu yet, but apparently it's over
Mm.
there, which is kind of cool.
With the one we said mu equals to okay, yeah, sure, we don't really know that value.
So believe it or not, mu is actually included in the definition of the theory.
Oh, okay.
Definition of the path integral. So this is why the path integral is a bit weird.
I see.
But hey, at least we have the cool part over here. But anyway, long story short, the problem that we were trying to address from the beginning was to calculate the determinant of the Jacobian. And as it turns out, the determinant of the Jacobian was just 1. Because, as we calculated, delta squared 0 was equal to 0. So, like, determinant J was equal to 1. Yay.
Hmm.
Well, like that's just how it is. So the takeaway here is that path integrals are a bit weird. But
I
that's
see.
just how it is.
I have a small question, which is for the regularization procedures. We
Yeah.
take f equals to 0, and we take epsilon, the limit as epsilon approaches 0 as well. Would I suppose the order would matter, right? The order in which
Yeah.
we take the limit.
Well,
So
technically speaking, we never actually took epsilon goes to 0 entirely because we couldn't. Actually, we couldn't really take any of those limits. But
I see.
In the end, those, if there are any like divergences, they cancel with other things in the theory so that everything is well defined. And that is actually what like renormalization has to do with. But that is for another time. And at least right now, like it's not really that important. So I would like to mention that renormalization is only defined perturbatively. To the extent of current human knowledge. But perturbative quantum field theory is rigorously defined. So, in fact, renormalization, as it is known today, is one of the most rigorously defined parts of quantum field theory, which might sound counterintuitive, but that's just the way it is. The book by Kevin Costello illustrates that. However, renormalization has never really been like extended beyond perturbative quantum field theory and like into non-perturbative effects. So this leads to the fact that basically perturbative quantum field theory with renormalization and all that is rigorously defined. Non-perturbative quantum field theory, generally speaking, isn't defined. So the only well-defined quantum field theories, non-perturbatively well-defined quantum field theories, are ones that have trivial normalization group flows. Those quantum field theories are usually conformal field theories or topological quantum field theories. So moral of the story, the only mathematically rigorously defined quantum field theories are two things: topological quantum field theories and conformal field theories. And also, I guess, free field theories. Because free field theories might not be conformal field theories, but they still have like trivial renormalization group flows. But these are like the easiest things in the world. It's a Gaussian path interval, so it's easy. And like supersymmetry can usually be included in these.
I see.
So the moral of the story is, if you want to do physics mathematically, this is all you need to know. But it's still a lot. Everything else, really all that's known are some limits of the theory.
See. Cool. Regarding the renormalization group, I just want to just check some of my understanding. From what I understand, there are parameters inside. Whenever you have observables, right? Whenever you have theory, there's going to be some parameters, for example, mass, coupling, and so on. Observables would then depend on these parameters. They're dependent on these parameters, and typically, in the context of in renormalization, usually we're talking about scale. So you usually I know there are a few methods of renormalization, but one of them is the Wilsonian, where you put a cutoff for the momentum decay.
Yeah.
And usually they put it in the higher limit, right? So it's a UV. It's a renormalizes the UV aspect.
Yeah.
And by putting this cutoff, you get a theory where so you integrate some integrand and your observables are now dependent on this cutoff. So they'll get I'll just call them O. They'll depend on your parameters and as well as the cutoff. But then there's a way to redefine the parameters. So we can say maybe M prime and G prime and have and essentially absorb the dependence of the parameters of the theory into absorb the dependence on lambda or on the cutoff into the parameters, and these will give you essentially a vector. This will tell you how the parameters M and G, how they flow when you increase lambda. So if let's say you increase the cutoff, it flows in this direction. This will give you a vector field essentially, and then that's where you have the fixed points where they could lead to somewhere, and from what I understand, if you have something that is scale invariant, how that ties in conformal field theory is if you have a scale invariant thing, then your parameters essentially wouldn't depend on the lambda. So they have trivial renormalization group. Right. How about topological field theory?
Well, nobody really. Well, I mean, like, you really don't like topological quantum field theory doesn't even have a concept of distance because it's topological.
Right.
So, like, yeah, I mean, renormalization has nothing to do with it. And like the renormalization group is really attractive as a physical idea. But honestly, like from a mathematical perspective, it's really not that much. It's just an idea. It's just a physical idea, but it's just really annoying to calculate. And honestly, that's why it's not that beautiful, in my opinion. But this is
I
just
see.
coming from me who's super math oriented.
Mm. Is it
So
right to say that in the past when people talk about renormalization, it was generally a procedure that was somewhat frowned upon until the renormalization group came along and helped kind of explain everything in context?
well, yeah, I guess. But I mean that's just explaining. I mean, like, physicists are always like arguing that some things are non-physical or whatever.
Right.
But like the physicist claims are always they're not like mathematical claims, so they're always like very subjective.
Mm.
So I
Right,
don't
right.
really care about them that much.
Okay. In some sense, the renormalization group had helped increase the acceptance of the renormalization procedure,
Yeah.
right?
Like
Yeah,
the way
okay,
I
sure.
see it, like I don't think anybody really cares about whether or not renormalization is valid anymore because it obviously is. And people don't
Mm.
even talk about non-normalization anymore. So if you were to ask someone like from like 40 years ago why quantum gravity was an unsolved problem, they would like mention renormalization right away. But
Mm-hmm.
nowadays everyone knows that renormalization is not the problem. The problem is
Oh,
that
okay.
gravity is weird. Um
I see.
because you're like quantizing the geometry of space-time. So there is no background geometry, so it has to be a topological quantum field theory. However,
I
nobody
see.
has found a topological quantum field theory with black holes yet.
I see.
That's the problem. That's the
I
problem with quantum
see.
gravity. The quantum gravity
Ah,
is just a
okay.
topological quantum field theory with black holes.
I see. I
Um,
see. That's interesting.
so yeah, my take on this is that quantum quantum gravity probably won't be solved until we have a super good understanding of even the very basic and well-defined quantum field theories like TQFT, CFT, etc. Um, Another thing to mention is string theory. String theory, I guess you could say that string theory doesn't need renormalization because all the infinities are cured in string theory. But
Mm-hmm.
the problem is string theory is also only perturbatively well-defined.
I see.
So it's only well-defined in some limits.
Mm.
Um,
I'm just wondering how much of string theory have you studied?
I wasn't interested in perturbative string theory, so that ended
I
up with
see.
me not really studying much. But like all
Ah,
the like
okay.
richer aspects of string theory, like duality, can also be understood within the context of quantum field theory. So I was like, why not just study quantum field theory instead?
I
Um,
see. I see. Okay.
but yeah, the key is that string theory is an unknown structure. It might not exist. It might just be a red
Mm.
herring, even mathematically, although I don't believe that's the case.
Mm.
At least quantum field theory, we can assume that quantum field theory is some kind of infinite dimensional integral. Um,
Mm.
you have that kind of idea. In string theory, nobody even knows what that is. Like there is not really a path integral. Nobody
Mm.
really knows what it's gonna be. But then
I
like
see.
Juan Maldacena come up with the ADS-CFT correspondence, which says that string theory in some cases is just isomorphic to some QFT.
Mm.
So yeah, apparently all we need to know is QFT because QFT also contains all of string theory somehow. And well, not all of it, but
Mm.
most of it. But and meanwhile, you can consider why not strings and what about branes? Like
Mm.
well, quantum field theory is like point particle theory, so it's like dot theory. I guess it's a point theory.
Mm.
But we have string theory. Why not go to higher dimensional objects and consider brane theory? Well, branes are in
Right.
string theory.
Mm.
So like string theory is the end all of like this kind of physical theory structure. But then again, it's dual to a quantum field theory. So what we see is that essentially quantum field theory, understanding quantum field theory is the end all of
Mm.
at least what has been worked with up to now. But so basically, it would be very prudent to study the
I
quantum field
see.
theories that we can rigorously
Oh,
understand, which is
but is it right?
TQFT, CFT,
Is it
free
right
field theories.
for ADS-CFT? Is it right to say that every string theory is dual to some quantum field theory, or only
No,
some?
no,
Only
it has
some,
to
right?
be a string theory on an ADS background.
Oh, is it? But is it true that all string theories on ADS background is dual to QFT or CFT?
Yeah, I think so. But
I
but
see.
nobody knows, like, the flat space case and the closed universe case are still very open problems, and I don't think
I
any of the
see.
physicists have come up with very compelling arguments for those. But if you
I
go to
see.
like very simple toy models of quantum gravity,
Mm,
doing quantum gravity in, for example, a closed universe can be easier, but those are just
mm.
toy models. And those toy
Oh,
models should only really be indicators of some physical um, effects that might happen in more complicated models. But yeah, from a mathematical perspective, there's still a lot that isn't understood even in quantum field theory. So
ADS space, inside a black hole, it is ADS, right? Outside the black hole is DS, right? Is that right?
well, no, that's a very crude way to put it. I don't think so.
Oh, okay. Then what's the um?
ADS is
Oh,
just a space.
I see.
ADS is
Okay,
ADS.
sure.
Um, I guess maybe we could talk about that in another video. I don't know.
Hmm. Okay, yeah, sure, sure. Let me see. I have a bit more time today. Um,
I don't think I have though, but at least we got that nice quote.
yeah. Okay.
That's a very
Yeah,
good quote.
that's
Um,
a quote by.
and now
So there's a
like
tongue.
now there's like yay, and now there's evidence that I'm the guy who came up with it. But like yeah, I like that quote.
Yeah. Okay.
Hmm.
Yeah, okay, thanks for I suppose you have to run off, yeah. Thanks
Yeah.
for the lecture. Let's take
Yeah,
the
I
time.
mean like yeah, let's keep doing this. Next week
Yeah.
I'll have time. Okay, cool.
Hmm.
See you next time, I
Okay.
guess. I'll stop recording.
Yeah. Thanks. Bye bye. Thanks.